Hello, everyone. Thank you for coming. Today we have Roman, who is talking to us about some biology topics mainly, I think. And I hope that at the end of this lesson, all of us mathematicians will know, maybe know if we have the right to think that biology and physics is just applied math.
Yeah, so hello everyone, my name is Roman. I'm here to present you on the topic of chaos, drugs, and cyborgs. I swear this is about science. The laser pointer seems to not be working, but I think we'll manage without it anyway. First of all, a little bit about me. Don't worry, I'm not gonna try to show myself as some great guy or something. I'm a fifth semester biology bachelor. I still like math and physics. Yes, we do exist. I do a lot of electronic projects in my free time, and I'm a staunch believer in transhumanism. If you want to debate me on that at the apero, please go ahead. I'd be very happy. Yeah. Anyway, let's dive straight in. Part 1, chaos. But we're not actually going to start with chaos. We're going to start with models. You know models. I mean, modeling is amazing. We can't, unfortunately, capture the entirety of our universe, so we always have to simplify. And there's a great quote that all models are wrong, but some are useful. And I'm just going to show you real quick how you make a basic model. First of all, you need to define a boundary. So what part of the universe are you actually going to be looking at, and what part are you not interested in? Inside this boundary, there's of course going to be processes which you're going to have to describe. And there's also, not necessarily, but there might be exchange fluxes with the outside world, and most interesting models will have those. And also you need to define an initial condition because a lot depends on the initial condition. I'm a biologist. I like animals, so let's do something biology related. We're going to make a population model. And I want to keep this as simple as possible, so I'm just going to throw the exchange fluxes, don't need them. System boundary, we're going to have a non-migrating population, so we're just going to look at some part of the world where there's a population. And what can happen to this population? Very simple. Individuals can either be born or they can die. Yeah, and we're going to use this formula to model this. It's very simple. The first part, the green part here, is individuals being born. So you can imagine this as a pair of rabbits copulating and having a bunch of beautiful children. For example, if 2 rabbits have 4 children, then R is going to be 2, and every generation the population is going to double. This would, of course, lead to exponential growth, and very quickly we're going to have a planet full of rabbits, which is why we also have this second part of the term, 1 minus xn, which 1 is just the maximum amount of population that our environment supports, and x is always going to be a fraction of how much of this environment is filled. And the more rabbits you have, the more they compete for food and the more they die. Right. We also have to define an initial condition. In this case, I'm just going to have it at 0.1 at some arbitrary value. As we will see, for small r's, it doesn't really matter. It's all going to go in the same direction. And we're going to play around with r a bit and see what we can get. So for r 1.5, we get this beautiful graph. As you see, we start at 0.1, so a 10% population, and the population will slowly grow until it reaches a certain point, and it will stay at this 1 point indefinitely. I created an animation showing what happens when r is between 0 and 1. You can imagine that for r between 0 and 1, it just means that the species actually produces less offspring than adults. So eventually, even without the environment, it's just going to die off by itself. And I mean, the environment is going to help with that. So you can see how the closer we get to 1, the closer we get to the population actually reaching a stable point above 0. For r between 1 and 3, it looks pretty, normal, as you'd expect. The higher r is, the higher our population. And oops, let me go back. And at some point, you'll see what actually happens is that the population overshoots and then a lot of population die, and it kind of starts like oscillating back and forth until it reaches, it settles at a certain value. But the closer you get to r equals 3, the more you will notice that it actually it takes longer and longer to actually settle at one specific value. And if we then go to some extreme values above 3, we're going to notice that it never settles at a specific value. It's always going to oscillate between two values, which is actually a phenomenon we see in nature as well. But the higher we go with r, closer to 4, you see some interesting stuff happening. So for example, about here, you're going to get it oscillating between 4 values, and then at 8, and then it goes into complete chaos. Just like, doesn't even make too much sense looking at this. We can't really infer anything from it, but we can make a nice plot. Down here, you see the r value, and on the y-axis, you see the value the population actually ends up at. And between 1 and 3, you get this graph, which is approximately as you would expect. The higher r, the higher the population, the point the population settles at. Then you get this oscillation between 2 points above 3, then between 4 points, and so on, then goes into complete chaos. Congratulations, you just had an introduction to chaos theory. If we actually zoom in on the last part between 3.5 and 4.0, you can really appreciate just how intricate this graph is, and that even though it devolves into complete chaos at certain points, it actually goes back to jumping between just 6 values here or between just 3 values here, for example. Right, now, I assume you've all seen this at some point in your life, I hope. If not, look it up. This is the Mandelbrot set. To get it is actually very simple. We look at the imaginary plane, and for every point on this plane, we apply this formula. And so I can show an example. We look at point number 1, which is way over here. So for the 0th iteration, z0 equals 1, of course, then so the formula is zn plus 1 is zn squared plus c. C is the initial number you chose on the complex plane. 1 squared plus 1 is 2. Then next step, 2 squared plus 1 is 5, and so on. I think you can see that this quickly just goes into infinity. And every point which goes into infinity, one way or another, is not part of the Mandelbrot set, and every point which doesn't is part of the Mandelbrot set. So let's look at the point which is in the Mandelbrot set. For example, -1, right here, right in the black. -1 squared, -1 is 0. 0 squared is 0, -1 is -1. And you can see it starts oscillating between -1 and 0. So what we can actually do, this is a 2D representation. We can do a 3D representation where we plot a third axis as the point, the value at which this point eventually settles in. So for this point, -1, we would actually have 2 points on 0 and on -1. And I hope this works, because I have an amazing demo for that. Might take a while to load. Fingers crossed. Yes, perfect. All right. So the Mandelbrot set, you'll recognize this. And when we go to the 3D view, again, remember that this is the point -1. We had 2 values here, as you can see. And this you might recognize. This is actually the logistic map we just looked at. So I just found it quite interesting that these two are so closely related to each other. And here for reference again, logistic map, Mandelbrot set. Yeah, with that, we're actually done with the first part. We're going straight to the second part, drugs. Yay. But for now, we'll actually stay with models. Sorry to disappoint you. And this is a publication which isn't actually that far back, from 2018. I think you all know the food pyramid, right? So at the bottom, you have this big chunk of producers like, I don't know, plants, for example, which then get eaten by herbivores, and then we eat the cows. And the further you go to the top, the less and less alpha predators there are. And this is true for terrestrial systems. They are way more producers than consumers. But in the marine ecosystem, it's actually inverted. So there are more consumers than producers. And you're like, okay, how does that work? Well, we can model it. So we define our boundary as one ecosystem. We're just going to look at, in this example, the marine ecosystem. And we're going to assume that the total biomass of producers and consumers is enough to model this ecosystem. So what actually happens there, it's very simple. Producers can gain biomass by photosynthesis, for example. They can get eaten, and they can die. And for consumers, it's even easier. They can either eat or they can die. So let's do this a bit more mathematically. We can set up mass balance equations. Yay, differential equations. Who doesn't love? hate them. For any node here, it's actually very simple. Everything that goes in is a positive part of the equation. Everything that goes out is a negative part. So for the producer, them gaining biomass through photosynthesis is positive, and them being eaten or dying is negative. And the same goes for the consumer. Them eating producers is positive, them dying is negative. Right. I don't actually like differential equations, so I'm going to get rid of them pretty quickly. We can do a steady state assumption, which is perfectly fine here, because we can assume that over the past couple of years, probably not much has changed in this distribution of biomass. So, of course, the derivative is 0, because there's no change, so we can get rid of that. And then you might notice that in this part of the equation, there is PT everywhere. So we put that outside of the scope, and CT as well. And since it's equal to 0, which can just divide by PT, we get rid of PT. And here we can divide by CT, so the consumer is depending on time, and we get rid of them. And then you just solve for the rest of the equation, where you just have either a CT or PT. You get these results. And then what we were interested in is the, the relative quantities of the consumers to the producers. So you divide the consumers by the producers. You get alpha minus delta P divided by delta C. What does that actually mean? We want producers with very high productivity, which are also actually long-lived, and we want long-lived consumers. What we actually see in the real world is, yes, indeed, high productivity for producers and long-lived consumers, but we actually have relatively short-lived producers, but they don't really play that big of a role. What's most important here is the ratio between the productivity of the producers and the longevity of the consumers. Right, let's actually apply this to something useful, and we do actually do this in biology. It's called flux balance analysis. What you see here in the background is a metabolic map. A metabolic map shows every single a metabolic map of an organism shows every single metabolite in this organism, and the fluxes that connect these metabolites. So, say a metabolite would just be a certain molecule, and the fluxes would be the reaction that either create this molecule or that use this molecule. So if you look at the single molecule, we have some reactions going in with reaction speed v1, and some reaction using this metabolite with reaction speed v2. And again, we can assume steady state over normal timeframes, like say a couple minutes. There's probably not going to be a lot of change in the concentration of metabolites in your body. So again, minus v1 plus v2 has to be 0 for steady state to be achieved. And if you look at a very, very simple metabolic map, this is an organism with 4 metabolites, A, B, C, and D. And the environment has these metabolites as well, because the organism takes up A and B from the environment and turns it into D and then releases it into the environment. And with metabolic maps, you're always going to have an underdetermined system because there's way less metabolites than fluxes. I mean, I think makes sense. Every metabolite can have a lot of reactions going in and a lot of reactions going out. We can look at this very mathematically. We can create a stoichiometric matrix where every column is a reaction, and every row just depicts what happens with this metabolite in this reaction. So our A is the organism taking up the metabolite A from the environment. That means we put a 1 on the A and a 0 on everything else because nothing happens to these metabolites. Or for reaction 1, for example, A gets used up, so A gets a -1, and C gets produced, so C gets a 1. B gets produced, so B gets a 1. If, say, it would produce 2B, then there would be a 2. I mean, I think this makes sense. Right. V is a possible flux distribution. I just chose one example here. For example, we could have a 0 at reaction 1. That would mean that reaction 1 doesn't happen at all. That means that the organism takes up A from the environment and turns O of the A it gets into C, and it also takes up B from the environment, and it turns O of the B that it gets from the environment into D. Right, since we assume quasi-steady state, we can actually try to solve this. So the stoichiometric matrix times the flux distribution has to equal 0. Of course, there's a boring solution where the flux distribution is 0, like there's nothing happening in the organism at all. That means it's probably dead, so we're not going to look at that. Yeah, like I already said, we're going to be working with underdetermined linear systems here because there's a lot more fluxes than metabolites. And the number of variables is given by n, which is the number of fluxes minus the rank of the matrix. So in our specific case, it would be 6 minus 4 is 2 variables. Yeah, the solution space is called the kernel or the null space of the matrix. And again, it's just linearly independent vectors. If you multiply the matrix by them you get 0. So for this case, these are 2 linearly independent flux distributions. And if we kind of use them as, I think they're called identity vectors, you actually get the solution space. So every single possible solution is a linear combination of the columns of K. Right. Of course, a solution space isn't actually going to do us a lot of good. We're looking for a specific solution or a number of solutions we can use it. So since we're always dealing with underdetermined systems, we're always going to get solution spaces. And to limit them, what we usually do is apply certain constraints that could, for example, be a maximum speed of a reaction or a directionality of a reaction, like some reactions are so thermodynamically advantageous that they can only go in one direction, they can't go back. And we're also going to optimize for something. For bacteria and fungi, for example, we can optimize for growth, so biomass production, usually a pretty good assumption. Right, how does it actually apply to drugs? I have to disappoint you, this is not about the good type of drugs, this is about the helpful kind of drugs. So say we have a bacterium and we want to develop a drug that inhibits the bacterium's growth. We're just going to write a very simple program where we can load the metabolic map. For example, we can actually load the metabolic map of the bacterium and the human. We look at some fluxes or a combination of fluxes and set these fluxes to 0. So we pretend that we inhibited them; they're no longer happening. We run the the flux balance analysis to see which alternative paths maybe the bacterium could take to still produce biomass. And only if the growth equals 0, that means that probably the bacterium is not going to grow. Well, I mean, pretty obviously it's not going to grow. So we can save these fluxes as a potential target for inhibitors. And we can also actually check if the human cells can still grow with the same inhibitors to see if we can find drugs which maybe affect bacteria but don't affect humans. So yeah, this is actually how you can mathematically find drugs. Pretty nice in my opinion. Yeah, and part 3 is cyborgs. So let's see if I can do a little demonstration. This is actually not a very scientific necessarily part of the presentation. This is more of like a novelty, which I wanted to include, because why not? Just so you can see what's out there. We don't have a document camera. Okay, never mind. I think you can see it like this. So I have 2 coins here, euro cents actually. One is a 10-cent coin, one is a 5-cent coin. With the 10-cent coin, nothing happens. With the 5-cent coin, I can do a little magic trick. Ooh, you see the coin is floating. Why is that? I actually have a magnetic implant, which I implanted in myself to fuel magnetic fields around me. It's pretty cool. And you can ask me all about it later. And the question I get asked the most is, what happens if I have to get an MRI? Will it just like rip out of my finger and I'm going to die? Well, if you look at the magnetic field in an MRI, so 1.5 Tesla is the older machines. Nowadays we have 7 Tesla machines. The magnetic field inside the machine is actually uniform. And from outside, I guess we could approximate it like a huge bar magnet. So let's look at what actually happens inside the magnetic field. Magnets have an interesting property that there's actually no magnetic monopoles, there's only magnetic dipoles. So inside a uniform magnetic field, a magnetic dipole is actually not going to experience any force on the entire magnet. There's only going to be torque acting upon this magnet, which can be calculated as the magnetic moment, cross product, the magnetic flux. In this case, we're not actually interested in the vector of the torque. We just want the magnitude of the torque to see if it will hurt or not. So we can do this by just having the magnetic moment times the external magnetic flux times sinus theta. We're going to assume worst case solution that the magnet is perpendicular to the magnetic field, so it really wants to turn. And then I run into a problem. There's tons of perfect documentation online on how to calculate magnetic moments of coils, but for permanent magnets it's actually very hard and imprecise, but you can approximate it with this equation, 1 over mu0 times the residual magnetic flux. Residual magnetic flux is what happens when you apply a magnetic field to an object and then take it away. It's going to emit a residual magnetic field for a short moment. And the residual magnetic flux of neodymium, which is what the magnet is made of, is approximately 1.3 Tesla. And there's also an interesting fact about materials in general. They can saturate magnetically. So even if I put this neodymium magnet in a 7 Tesla magnetic field, it's not actually going to create a 7 Tesla magnet because it caps out at about 1.3 Tesla. Yes, and V is just the volume of the magnet, so I calculate that. For my small magnet, I get 0.0443 ampere meter squared, and the torque is then going to be about 0.3 Newton meter for a 7 Tesla magnetic field, which, I mean, you can put approximately 2 Newton meter of torque with a small electronics screwdriver, so 0.3 is not that much. It might hurt, but remember, your skin is also pretty flexible, so the magnet isn't super stiff in there, so I don't think I'm going to be killed. But much more interesting might be what actually happens when I approach the MRI machine. But I mean, 7 Tesla is a lot, right? And for this, we have this formula that the force is the gradient of the magnetic moment times the dot product of the magnetic moment times the magnetic flux. And the gradient is just the change in quantity in the direction of the fastest change. In this case, we can just take 2 points because we know the direction of the fastest change is towards the magnets. So we take 2 points and calculate it. And since it's a dot product, you might be smart and think, hey, dot product, that's magnetic moment times magnetic flux times cosinus theta. So if I just orient the magnet perpendicularly, then there's not going to be no force at all, right? Yes, in theory, but the external magnetic field can actually magnetize the magnet as well. So we just create a magnet which is looking in the direction of the magnetic field anyway, so it would still pull. A bit less force because the magnetic it's not symmetrical. It's actually, it is symmetrical. It's cylindrical. So in perpendicular direction, it would have a bit less separation between the magnetic poles. So it might be a slight difference in force, but we're just going to ignore that. It's not much. So again, we calculate it for, say, these 2 points, 500 millitesla and 1 millitesla. That's a change of 500 millitesla over 1.5 meters. And the force we get is 0.014 Newton, or 1 gram of weight. So not very much. But that's not the strongest force. At some point, it's going to go from this 1,000 millitesla to actually 7 Tesla inside the coil. And if we just assume that it happens over half a meter, maybe it's a good assumption, maybe not, maybe it's a bit more or a bit less. But the approximate force you would get is 500 and 0.5 Newton, so approximately 50 grams of force pulling on the magnet, which might be a bit painful, but I don't think I'm going to like literally get it ripped out of my finger. Yeah. Anyway, unfortunately, this is already the end. I know you're all very sad. Some acknowledgements. There's some guy on GitHub who actually wrote the 3D visualization of the Mandelbrot logistic map. That wasn't me. And also thank you very much to Uwe Sauer, S. Brüning, Jay Stelling, and Anne Zamboni for the systems biology course, which I took a lot of concepts from for the drugs part. And with that, thank you very much for your attention. Yeah. Yeah, and if you have any questions, now's the time. Yes, please.
Do you have the XG3 injectable biomagnet or the Titan sensing biomagnet?
No, it's something else. It's a cylindrical magnet with a silicone covering for biocompatibility.
Is your finger swollen?
No, I mean you can check it out. It's like if you press on it, you can slightly feel the magnet, but it's not swollen or anything. It actually healed within 3 days after incision, right there.
And you feel like a tug, right?
Yes, exactly. So if it's a constant magnetic field, it's a tug, and if it's a changing magnetic field, say from a transformer, then it like vibrates, and you can feel it here. So microwaves actually have very big, I think like 2 kilowatt transformers. Oh no, sorry, no, the 800, 900 watt transformers, and I can feel them from like half a meter away. So, yeah, quite sensitive actually. No, I went through security dozens of times. It never did anything. Yep.
What does this mean about security?
True that, yeah. So, I mean, there are 3D printed guns which only have like a tiny nail in them, plus the bullet, of course. Not sure if that is going to trigger a magnetic like detector, but you didn't hear that from me. Yeah. It's the idea that we should strive towards actually changing humans, so either genetically modifying them. So there's kind of 2 different camps of thoughts. Either we genetically modify humans to make them like stronger, better, faster, or cybernetically enhance them. As a biologist, I of course am a big proponent of the genetic modification camp. I think that cybernetics are quite very, very far away from actually competing with biological systems. Yes.
What are the possibilities of expanding our senses currently available?
Right now, expanding senses actually, unfortunately, not much. Drugs, yes, exactly. That's always an answer.
But do you feel like you have a sixth sense with this device?
Yes, you could call that a sixth sense, maybe. It's still like you feel it as a pull, so I guess it's equivalent to just, touch, but you expand what you actually feel. So maybe not right now, but some humans actually have a 4th color receptor molecule, so you could maybe genetically modify the eyes of some human to have this 4th color pigment, which would allow you to see slightly more in the UV range. But that's all like future stuff. So right now, very limited possibilities, unfortunately. Yes. Anybody else? Yes, please.
How legal is it in Switzerland to just implant yourself some magnet?
Well, there's the 2 shops and body mod shops, and they do it perfectly legally. It's not much different from getting, I don't know, like a piercing or something. So I actually had to go to a tattoo parlor to get it done. So the way I stumbled across it, like I knew about it, and I was like, I had this thought in my head, hey, maybe I should do it. And I stumbled upon a website which has like a handful of people who do magnet implants, and I saw that there was one in my city, and I'm like, what a coincidence. Why not? I'm going to do it. So it's done without anesthesia, unfortunately, so you have to endure the pain. But it is perfectly legal. Yeah. Yes, please.
The magnet will get weaker over time. Is that true?
Yes, that is true.
Then could you maybe like make some implants that like somehow takes and current or energy from the body to maintain the magnetic, or like you just have to replace it?
I'm probably going to have to replace it. So what you're saying is like maybe using body heat to charge a coil, I guess. So the issue is with coils that to even approximate a field as strong as a neodymium magnet, they'd have to first of all be a lot larger than the neodymium magnet, and they could also accomplish it only with pulses. So you'd have to like have a 100,000 amp current pulse going through a magnet, then shortly it would be a strong magnetic field. But that obviously doesn't work in the body, so unfortunately, it's permanent magnets are the way to go. Yeah, but I've had it for I think 2.5 years right now, and it's still going very strong. I can still lift a spoon. Don't have one with me, unfortunately, but yeah.
Okay, I think
Or yeah, final question, sure.
I think we can go to the apero because everyone's hungry and we have a lot of questions. You're coming to the apero, right?
Yeah, of course I am.
Okay, then see you at
Won't miss that.
Here's a spoon.
Oh, okay. So the thing is, like in restaurants, I can actually differentiate between cheap silverware and expensive ones. Yeah, okay, that doesn't work. That's the expensive one. Is it yours? Yeah. So steel actually is only magnetizable if it has a pretty low chromium content. As soon as it's like very properly stainless and has a high chromium content, it's non-magnetic. But yeah. But here in the Mensa, for example, they have very cheap cutlery, so that works perfectly. Yeah.